Hello, and welcome to the Chapter 16.5 lecture on triple integrals in spherical and cylindrical coordinates. So, last time we talked about how to find triple integrals in ordinary Cartesian coordinates. However, for many surfaces, such as cones or surfaces like this, it will be much more convenient to slice it into cylinders. So we'll have cylinders like this going up, and we can integrate that way radially going outward. And that will be much more elegant than doing it in Cartesian coordinates. So let's begin just with a kind of more conceptual example of finding the volume of this cone. So we can slice it into cylinders. The picture would look like this. So we can slice it into cylinders like this for various radii r. And first, what is the area of the cylinder? Well, we can take it and unfold it, and this would be the circumference, which is 2 pi r, and this is the height h. And what is that height as a function of r? Well, you can see that this line, it goes from 1 down to 1, slope of -1. This is the line z equals 1 minus r, where r is the radius away from the origin. So that's what the h is. And we can find the total volume under this by adding together all of the volumes of tiny shells. So what we can do is add to this cylinder, which is right now just an area, a small dr, and that dr would give it a small volume, like that. And we can then add together all of those volumes. And this volume would be the area times the width. So the volume would be, therefore, the integral from 0 to 1 of 2 pi r times 1 minus r dr. And we can write it out as an integral like this. An integral, this elongated s, that remember means a sum. So we're summing the volumes of all of these shells as r goes from 0 out to 1. And the volume of those shells, that's the circumference times the height, that's the area, then times dr, the little thickness to give it a volume. And we're adding those together from r 0 to 1. And if you evaluate this integral, then you'll get pi over 3. The step skip there, this is just a calculus 1 integral, actually. You FOIL out as a polynomial, and you can do that, you'll get pi over 3. So the point of this was to illustrate integrating by cylindrical shells. Now, in this example, through thinking about geometrically, we were able to write down a calculus 1 integral off the bat. But in other cases, we might want to integrate a function f of x, y, and z over some volume that is circular in some sense. So we need a more general method than this. First, we need to talk about cylindrical coordinates. Cylindrical coordinates are fortunately very simple, given we understand polar coordinates from the previous section. So in Cartesian coordinates, we have x, y, z. Cylindrical coordinates just means r, theta, z. So we take the polar coordinates on the xy plane, and then we can slide up or down on the z-axis. And integration in cylindrical coordinates will be dz, dr, d theta, and it works like this. Perhaps I should show a picture first. First, we'll integrate dz, so going along this green, starting from an arbitrary r comma theta. And then we'll integrate that dr, moving from our starting r to our outer radius. And then we'll integrate d theta, swiveling that around. And in total, therefore, we'll integrate over the whole volume. And that's what this says. So we'll have our bounds on z, our bounds on r, and our bounds on theta. And we need to convert our x and y to be in terms of r and theta first. So this is converting to polar coordinates on xy. That's all that cylindrical coordinates are. The z is preserved. We integrate that dz. Don't forget this r right here that always occurs in polar coordinates. We always need to add that in for polar coordinates because after we integrate dz, then what remains is polar coordinates. So we have that r there, and then we finish integrating dr d theta. So I should point out, once we are done with the inner integral, then it's just polar coordinates from there on out. We're then operating just on the xy plane, which is now the r theta plane. Let's do an example. So say we have a paraboloid, this paraboloid, and we have a variable density within it. The density is given by 5 minus z. Let's find the mass. So we know that the mass, that's density times volume, and therefore total mass will be the triple integral of density dv over the region, whatever it is, in this case, this region. So what we want here is the triple integral of 5 minus z dv over this paraboloid. Okay, we need to find the bounds here. And if we did it dx dy dz or something similar to that, then we would have the circular bounds with the square root of 1 minus x squared. It's not pretty. But clearly it's nice in cylindrical coordinates, since this is a constant outer r bound, and so forth. Okay, let's set up this integral from the inside out. So first, the z varies from 0 up to the 4 minus r squared. That 4 minus r squared is just the formula for this particular paraboloid. And then we want to integrate that dr. And again, don't forget this r right here that you always need to stick in, because at this point we're in polar coordinates on the xy plane. Okay, r goes from 0, that's r equals 0, up to, what is this point? So we'll need to find these bounds often, and the way to find that bound. So when z equals 0, then we have 0 is 4 minus r squared, and that means that r is 2, solving, and that is the max r, which occurs on the xy plane. So that's why that upper r bound is 2. Right there, it's on the xy plane, z is 0. Okay, and then we integrate that d theta. What are our theta bounds? Well, we're swiveling all the way around. That's a full 2 pi revolution. So 0 to 2 pi. So that is our triple integral to evaluate the mass of this shape given this density function. So that's the setup. It's not too bad. And from there, we can evaluate that. Integrating 5 minus z dz, we have 5z minus z squared over 2. We evaluate that between 0 and 4 minus r squared. We wind up with this. Except without the r, we multiply it by this r here that we had to always stick in because of polar. And we get this, and then it's just a matter of calculus 2. Or calculus 1, in the sense that it's just a polynomial. All right. And sometimes we want to find volumes of regions bounded between two surfaces. And if it is of circular base in some sense like this, then that is screens for cylindrical coordinates. And we know that the volume, that will be the triple integral of 1 dv. And to do that in cylindrical coordinates, we'll need bounds, of course. But don't forget that in cylindrical coordinates, we don't have x's and y's. So really the first thing that we want to do is convert everything to be in terms of r and thetas only. So don't forget that first, you need to convert so that your x's and y's are r's and thetas only, because that is what you need in cylindrical coordinates, which are r theta z. So what's the square root of x squared plus y squared? Well, x squared plus y squared is r squared, so that's just c equals r. And similarly, this guy, that's 12 minus x squared plus y squared. So that's the same as 12 minus r squared. So that makes it much simpler looking, and that's a hint that indeed cylindrical coordinates were the right choice. So good, we have our upper and lower bounds on z in terms of r, and we'll also need what is the maximum r. So in other words, we're starting here, we're going out to here, and we're asking, what is the length of this? Out to what r are we integrating? Well, we can do that by finding the intersection of these two surfaces. So remember, this was z is 12 minus r squared, and this was z equals r. So the intersection of the surfaces z is 12 minus r squared and z equals r, that is where 12 minus r squared is r, setting the z's equal to each other, which is where r squared plus r minus 12 is 0. And factoring and solving for r, we have r is 3 or minus 4. Okay, and z is r, so we need a positive r, since where z is positive. So that means that the max r is r equals 3. So we answer that question. Our r will go from 0 out to 3. We're finding the bounds on the integrals. Okay, so z goes from r up to 12 minus r goes from 0 to 3, and theta makes a full revolution, 0 to 2 pi. So in total, the volume is this. So we have a dz r, dr d theta, and the 1 again is because of volume. That's what we always put in the triple integral if we're just finding the volume. Okay, so z goes from this lower surface of z equals r up to this upper paraboloid of 12 minus r squared, since we converted everything to be in terms of r and theta. So our bounds there are r to 12 minus r squared. R goes from 0 to 3, as we just found, and theta makes a full revolution, 0 to 2 pi. And that's it, as far as the setup is concerned. So from here, it's just an iterated integral. We integrate this dz, that's z evaluated between z equals r to z equals 12 minus r squared times r dr d theta, etc. It's computationally very much like this example, so you can just refer to this example as a guide if you are uncertain how to do it. And recall that Wolfram Alpha can actually compute these for us. Don't become overly dependent on it, since the final exam, for example, is in person and you need to submit written work anyway for the upcoming midterm. And in this case, you would get 99 pi over 2, which is just a matter of plugging and chugging, extremely like this problem here. The important part is thus the setup. Let's do one more example. Go ahead and try your hand at this, actually. Pause the video, I encourage you to, and set it up. All right, so let's draw a picture. We have a cylinder, and the cylinder is cut off by a plane, which is at an angle, and that will cut the cylinder to be something like that. And we want to find the volume of this cylinder. So r goes from what to what? Well, r clearly goes to a maximum radius of 1, because this is the same as r squared is 1, i.e. r is 1 is the bound. And z goes from 0 to what point? Well, to this point. However, we don't want x's and y's, remember. We need to convert this to be in terms of r's and thetas. So x squared plus y squared is r squared, but an x by itself, that's not squared. What do we do? Well, recall transforming from polar to Cartesian and vice versa. It's just trigonometry. X is the same as r cosine theta, the adjacent, and y is the opposite on the triangle, that's r sine theta. So in other words, this maximum z here is this. Okay, and theta does a full revolution from 0 to 2 pi. So our triple integral in total looks like this. So because it's volume, we're integrating 1, and our z goes from z equals 0, because we're bounded below by z equals 0, up to z is 8 plus r cosine theta plus r sine theta. And then don't forget to multiply by the polar r, and then r itself goes from 0 to 1. And theta goes from 0 to 2 pi. So that is our setup. And if you compute that, you should get 8 pi. There's nothing hard going on with the integration. It's just basic trig integration, integral of cosine is sine, etc. Now, our last small topic is integration by spherical shells. In integrating by spherical shells, instead of adding together cylinders, we add together spheres. What is the volume of a sphere? That is 4/3 pi r cubed, as you might recall. And what is the surface area of a sphere? That is 4 pi r squared. Have you ever noticed that the surface area of a sphere is ddr of the volume of the sphere? The reason for that is that we can find the volume of a sphere by integrating the surface area dr by thinking of a integral in spherical coordinates where we add together these various spherical shells, dr. Let's do an example. We typically use rho for the radius of one of the shells, and this is the density of some planet. And we want the total mass of the planet. We know that the mass, as always, is the triple integral of density, dv. And the way we can think about this is we'll find the mass of a shell. A shell of radius rho has mass 5 minus rho squared, that's going to be the density, or is the density as given here, times its volume. The volume is 4 pi rho squared d rho, because this is the area of the shell, and then we can imagine a little d rho as the thickness of the shell. And in total then, this is the volume of the shell. Okay, so that will be the mass of one of these shells. And then the total mass of the planet will be the sum of the masses of all of these shells, and that's adding together all of these shells between 0 and 2, because the problem told us that r here is 2, of these masses. So of 5 minus rho squared times 4 pi rho squared d rho. Okay, so we found that the mass was the integral from 0 to 2 of this. Density times the volume of a shell, all added together between shells of radius 0 up to shells of radius 2. And that's just a calculus 1 integral. We FOIL this out, it's a polynomial. And computing that, we get 4/16 pi over 15. That's some steps skipped since it's just calculus 1. You FOIL out, it's a polynomial, integrate the polynomial between 0 and 2. And that concludes chapter 16.5. Have a great one.